Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week, and we're going to go all the way back to January of 1978 and talk about one of the worst weather forecasts I ever made and what I learned from that experience. Of course, I was in my infant stages back then, just being a junior at Penn State, but it had a profound effect on me, and I still look back on it very fondly now. You know, when things don't go right in the moment, you can't see the big picture sometimes. You can't say, oh, this is wonderful, I learned from this, but down the road, then you get some perspective, and you realize that, boy, I'm really glad I had that experience because I learned a lot from it. So that's what this is going to be about. I will warn you, it is going to get very geeky in spots, but try to stick with me on this because I'll try to make it as understandable as I can. And I hope you can appreciate my passion for this, even though it was so long ago. Okay, so let's do a little bit of introduction here. From January 13th of 1978 to January 20th of 1978, 3 major winter storms affected the east coast of the United States. At Penn State, we received almost 3 feet of snow in 7 days, and the university closed at 2 p.m. on Friday, January 20th, just after my last class had concluded, so I did not realize any benefit of that university shutdown. I was a junior at Penn State and was fortunate enough to be hired by a local radio station in Baltimore to provide them weather forecasts, and they paid me a whopping $50 a month. Now, in all honesty, back at that time, the National Weather Service was not nearly as well respected as it is today. There were a lot of people that were closing in on retirement. They were not comfortable with some of the newer technologies and the mathematical modeling and all of that. So they were just sort of biding their time until their career ended. Now, not everybody was like that. That would be a grossly unfair statement for me to make, but I do know of several examples of that. And so as a result, radio and TV stations were beginning to look toward either degreed meteorologists or people studying to be degreed meteorologists to provide their weather forecasts to them. In Baltimore, the first 2 storms had produced some snow at the beginning, but in both cases, the snow had turned to rain. And I had no doubt in my mind, the 3rd storm for Baltimore would be all rain. Boy, was I wrong. Now, we've talked about this before, and before we get into this, I just wanted to give you a little personal sidelight here. I had an exam on January 20th, and so I was at my apartment studying for that. And I get a call from one of my friends in the Weather Observatory, and he said, Greg, I just thought you'd like to know the visibility is 1/16 of a mile in heavy snow at Wallops Island, Virginia, which is southeast of Baltimore, right at the coast. And I said, look, I've got a test tomorrow. I'm not in the mood for jokes. Any other time this will be funny, but I'm just not in the mood. So, let's end this now and I'll see you tomorrow. And he said, Greg, I'm not kidding. And I knew at that point there was a problem. So I jumped out of the apartment, ran to the observatory, looked at the observations. Baltimore was snowing at the rate of 1 inch an hour, and it snowed for 6 hours at that rate, and they got half a foot of snow before it changed over to sleet and freezing rain. So we've talked many times about how the thickness between 2 constant pressure surfaces is proportional to the average temperature of the layer between them. So the ground is at the bottom, there's our 1,000 millibar surface, there's our 500 millibar surface, and obviously the thickness between the 2 is much greater on the left than it is on the right. And so the air on the left is warm and the air on the right is cold. You can think of the left as being the equator and the right as being the North Pole, if you would like. Now, back in the old days, the 1,000 to 500 millibar thickness was the go-to when it came to predicting the location of the rain snow line. It had been shown statistically that if one was near sea level, a thickness of 5,400 meters was likely to be the dividing line or very close to the dividing line between rain and snow. This became affectionately known as the 540 line. They just dropped the last 0, make it a little bit easier to say, and virtually all operational forecasters, knew exactly what that meant. I was just learning how to forecast the weather, so of course I was going to, I was going to use the 540 line in my rain snow predictions. It worked pretty well for the first two storms, but boy, did it hang me out to dry on the third one. So now we get into the geekiest part of the video, and just bear with me here. There is an equation in meteorology that describes a balance of forces between gravity going down and what's called the pressure gradient force going up. The pressure gradient force is what drives the wind, and it operates from high pressure to low pressure. And since the pressure gets lower as you go up, that force is directed upward, gravity is directed downward, and so you have a balance of those forces. That way the atmosphere doesn't escape into space or collapse into the ground. Now, there's another equation called the equation of state, and it states that the pressure is equal to the product of the density, which is represented by the Greek letter rho, times the gas constant times the temperature. Well, if you solve that second equation for rho, density, you get P over RT. And then you can substitute that back into the first equation, and you end up with dP over dz is equal to minus PG over RT. Now, this is what's called a differential equation, but all it means is dP dz means how is the pressure changing with respect to height, and then the other four variables on the right are simply those four variables and whatever their values are. So if you divide both sides of the equation by P and you multiply both sides of the equation by dz, you end up with dP over P is equal to minus G over RT times dz. Then in calculus, you can do what's called an integration of that equation. And so you integrate from P1, which is 1,000 millibars, to P2, 500 millibars. And you integrate the right side of the equation from Z1, the lower height, to Z2, the higher height. And when you do that, you end up with the natural log of P1 over P2 is equal to G over RT times Z2 minus Z1. Now, normally, when you look at that equation, the second one from the bottom, and you see P1 to P2, when you integrate that, then you would have the natural log of P2 over P1. But that's not what I have at the bottom there, right? Well, the reason for that is, if you want to get rid of that minus sign, that pesky minus sign there, you simply take the P1 and the P2 and you swap them. And so you end up with P1 over P2. So now it's 1,000 over 500. The natural log of that ratio is equal to G over RT times Z2 minus Z1. And Z2 minus Z1 is the thickness, or the distance between P1 and P2. Okay. We know that P1 is 1,000, P2 is 500, G is the gravitational constant, which is 9.8 meters per second squared, R is the gas constant, which is 287.05 joules per kilogram times Kelvin. Don't worry about what joules are. And temperature, we're going to assign as 273.15 Kelvin. All the equations in meteorology use Kelvin. 273.15 is the same thing as 32 degrees Fahrenheit, okay? The freezing point. So we take our equation and we plug all those numbers in. And we get the natural log of 1,000 over 500 is equal to 9.8 divided by the gas constant, 287.05, times the temperature, 273.15, times the thickness. When you do the math, you end up with that number there, 0.69314718006, is equal to 0.000124987 times the thickness. You solve for the thickness, and you get 5,545.72 meters. Now, let's increase the temperature by 1 degree Celsius, okay, or Kelvin. They're both the same. And we get these numbers, and when we solve for the thickness, we get 5,566.03 meters. Now, 1 degree Kelvin is equal to 1 degree C, and the difference between 5545 and 5566 is 20.30 meters. But a degree Fahrenheit is only 5/9 as big as a degree Celsius. So we have to take 5/9 times the 20.3, and we get 1 degree Fahrenheit is equal to 11.28 meters. So for every 11.28 meters that the thickness increases or decreases, the average temperature of the layer is either going up or going down by 1 degree Fahrenheit. So let's compare the 3 storms in Baltimore, or at least near Baltimore. The closest weather balloon is at Washington Dulles Airport, which is not too far northwest of Baltimore. So for Storm 1, which started as snow and turned to rain, the 1,000 to 500 millibar thickness started at 537.4, so it was below 540, and then ended up at 545.3, which was above 540, which makes sense that it changed to rain. The 500 millibar temperature went from minus 21.8 C to minus 17.6 C at the end of the precipitation event. Storm number 2 started off at 538.1, ended up at 543.9. So, started as snow, turned to rain. 500 millibar temperature went from minus 18.3 to minus 19.6. Storm 3, at the start of the precipitation, the thickness was 543.4 and ended up at 546.6, both numbers clearly above 540. And the 500 millibar temperature, compare those values to the ones you see in Storm 1 and Storm 2, considerably warmer, minus 14.8 C, and ended up at minus 13.1 C. Now, the 25th to the 75th percentile, okay, this is based on lots and lots of data over many, many years. The middle of the bell curve, if you look at all the data accumulated over all this time, the normal 500 millibar temperature at Washington Dulles Airport on January 20th ranges from minus 17.9 to minus 24.7. Most of the time, that is the range that you would see. However, notice again that the thicknesses both at the beginning and end of the storm were above 540, and the temperatures were unusually warm. The bottom of that normal range is minus 17.9, and these temperatures were minus 14.8 and minus 13.1. And remember, every degree Fahrenheit equals 11.28 meters. So if your thickness is 53 meters higher, and that's what I'm doing here between Storm 2 and Storm 3 at the start, that's equivalent to a 4.7 degree Fahrenheit temperature increase, average temperature increase throughout that layer, okay? Which is pretty significant. You all know that a couple of degrees either way can make a big difference when it comes to rain versus snow. So the conclusions that I had to come to were this. Abnormally warm temperatures at the top of the 1,000 to 500 millibar layer distorted the thickness values to higher values, putting them above 540. But abnormally warm temperatures that high up don't matter because it's always cold enough to snow at that altitude. Okay, so it doesn't matter that it was unusually warm. It was still cold enough to produce snow. The make or break portion of the atmosphere regarding rain versus snow is always, at least almost always, in the lowest 10,000 feet, and many times in the lowest 5,000 feet. So the focus over time has shifted to the 850 to 700 millibar thickness and the 1,000 to 850 millibar thickness. The first one roughly 5,000 feet to 10,000 feet, the other one roughly from the ground up to about 5,000 feet. So these layers are less deep, which means that you're not averaging over 3.5 miles the way you are with 1,000 to 500 millibars. And also, these layers are closer to the surface. You're not being contaminated by temperature changes at an altitude where it really doesn't matter what the temperature is. And so the 1,000 to 500 thickness or the 540 line fell out of favor. If anybody is still using that, I hope they see this video. But 1,000 to 850 thickness and the 850 to 700 thickness are the way to go. And there was actually a gentleman that worked at the National Weather Service in Raleigh, Kermit Keeter, who's now retired, but he, along with another person there, and I wish I could remember the name right now, but anyways, he actually developed a technique which was incorporated into an app that is used by forecasters all across the country. And it's a nomogram that actually takes a look at the 1,850 thickness and the 850 to 700 thickness, and based on historical data, gives you the best estimate as to what precip type will occur with the combination of those two numbers. And so this is a technique that has been really looked at and is still widely used even to this day. All right. That was over a 15, well, almost a 16-minute video. So I hope you found that somewhat interesting. Again, I hope you can tell that I'm passionate about this kind of stuff, and I find it fun to look back at these major events in my life that had a profound effect on me and my ability to forecast the weather. So I hope you found it at least somewhat intriguing. All right, folks, that's it for now. You all have a wonderful, it's probably going to be Thursday before most of you see this, so I hope you have a wonderful Thursday, and we'll talk to you later today. Take care.